What happens when I put this potato into this oven to heat up? Well, the potato is going to heat up, but it's important in a lot of applications to have a good model about how that heating is going to go. So that model could be used then to predict like how much insulation you need or something like that. So this is kind of a silly example, but it has a lot of applications, and it really shows how to use the mean value theorem and implicit differentiation to do interesting stuff. So here's the situation. This is a 40, call it a 52 degree potato. I've got my instant oven thermometer here. And well, let's see what's going to happen. If I'm going to put it in to heat up, oh, no. This is a completely different model. This doesn't heat things up by having hot air around the potato. This works on an electrical principle that's completely different. Nope, I need to put the potato into this oven, which has conveniently been preheated to 350 degrees. Okay, so we can start the experiment. As far as on the length of the video, what we're seeing here is we're a minute 32 in. Potato in oven. Let's get cooking. Okay. So here is how this model is developed. Yes, the potato gets hotter, and no, it won't get any hotter than the oven. So we know the temperature is going to go from 50 degrees up to 350 degrees, and it's probably not going to go like this unless you have a defective thermostat in your oven, but that's a different matter. So we have this idealization. So we're going to let H is for heat, be a function of T. Right now it could be a passive function. We just use the oven thermometer. Or it could be an active function. We want to make it an active function because a model is always an active function. Okay, and here's what the postulates are. If H is far from 350, so like it is just now, then the temperature should be going up pretty quickly. So that's the rate of change of temperature. So what we're going to say is that dH dt is big if 350 minus H is big. That's a pretty reasonable assumption, and experience has shown that this is a decent model, so that's good. Okay, and the other part of that is that dH by dt is small. dH by dt, remember, is the Leibniz notation for the derivative. T is the variable. If 350 minus H is small. That's just peachy. This and 89 cents will buy you a small fries at McDonald's, though. It's not worth very much because we need to get some kind of formula. And this is where the trickiness and the judgment comes in. And so here's the situation. We're going to assume that the variation between dH dt and this temperature difference is linear. That may or may not be a good assumption, but it's the assumption that people have been making for 400 years, and it seems to have worked out pretty well. You could assume other kinds of relationships as long as they're increasing, but this is what we've been doing so far. I don't know, should I check the temperature of the potato? I'm getting hungry. Instant read thermometer. Potato in oven. Oh, the temperature is going up. This can't be very exciting, can it? I'll tell you what, it hurts my hand. It's hot in there. All right, we're going to call that, let's call it 86. So we got 86 at 451. We'll just make some notes about that. and then continue to talk about what goes on. So here's back to our model, and what we're going to say is that all this kitchen stuff lying around, I'm getting hungry too, is what we're going to postulate here, and this is Newton's law of cooling and heating. There's a sign that's involved, so it works the same for both. So dH by dt, that's the Leibniz notation for the derivative of h when t is a variable. Remember, h is the temperature in degrees Fahrenheit, and is proportional. That's the linear assumption part, and we're just going to use 350 minus h. That's what we've been saying. So the rate of change of h is proportional to the difference between h and 350. And this works both ways. We're just going to assume that k is a positive constant here. That may not be valid in real life, but it's pretty close to constant. And so there's the situation. Okay, so this is a differential equation. It's an equation involving a function and its derivatives. And if you don't think they're mysterious, then there's something wrong with you. For the moment, we have no tools for solving this. So we're just going to have to use our heads, which is to say the mean value theorem, in order to solve or get some information about what's going on with this function. So all we can do is get some information. This is qualitative, not quantitative. Okay, so we've got the mean value theorem. So here's the situation. If 350 minus h is positive, so that would be where the temperature is less than 350, like it is right now, then that means that because k is positive, dH by dt is positive, and that means that h is increasing as a function of time. Well, that's what we expect. You put a cold potato in a hot oven, temperature goes up. Hey, we like that. Okay. So the other half of that is that if 350 minus h is negative, then dH by dt is negative, because dH by dt is a constant times 350 minus h is a constant times a negative. And that means that h is decreasing. We're just using the mean value theorem. H is decreasing. That's the mean value theorem. And that makes sense if you put this hot potato into the freezer, then h will be hotter than the freezer temperature, and the temperature will go down. Okay. Oh, maybe we ought to take another look. It's been about 4 more minutes. Hope I don't burn myself. Instant read thermometer, potato. Off we go. This is an experiment, by the way, so, I'm doing this right now, so we're just going to have to see what happens. And my hand is getting hot. That's definitely a thing that you would expect to happen in this situation. And it's so hot, I'm going to say that the potato temperature is 100 degrees. So that's at 8:42 of the video. And so, okay, let's go back to looking at the graph of this function h. So the interesting part here is everything's going to be happening around 350. If h is 350, the derivative is 0, so you have a constant function. The temperature of the potato should stay at 350. We don't usually cook them that hot. They turn to mush, but that's okay. Anyway, so what we're seeing here is that if h is above 350, then then h is increasing, and if h is below 350, then h is decreasing. So we're seeing graphs like this. This is real vague. That's all we can really do in this situation. Now, we know the temperature is not going to pass this 350 line, so there is going to have to be some concavity, and we're going to look at that next. So this is the behavior that we're expecting, and so let's see if we can push this on a little bit and see what happens with the second derivative. So the second derivative, remember, h is a function. We have to use implicit derivatives. and dH by dt is a function. So the second derivative means I have to take the derivative of this. Well, that is minus k times dH by dt. That's a pretty easy derivative. That's the kind of derivative that people take in real life. So, yeah, in real life, they don't necessarily get much harder than that. But dH by dt, we have an equation for that all in terms of h, so we're going to end up with I lost a constant someplace. K squared h minus 350. I flipped a sign. There was a negative there, and I flipped it. Okay, so now we'll see what's gone on, because that means that the second derivative has the same sign as h minus 350. So there's a second derivative, there's h minus 350. K squared is definitely positive, whatever k is. So what we're seeing is that if h is positive, then h is concave up. And if h is negative, then h is concave down. This is real calculus. Doing those derivatives that you might have seen in some books is not real calculus. That should be outlawed by the Geneva Convention. So I'm going to refine this picture because I know the concavity. And one thing I know is that the concavity doesn't change. So if h is positive, we're going to be concave up. You can kind of see that here. If h is negative, we're going to be concave down. And so here we go. Here's a concave up. That's in red because that's on the hot side. And a concave down. That's in green. And that's what the solution, h, looks like. And so if we had some more data, we might be able to fit things in. After we do some integration, we'll be able to do this exactly. But right now, this is telling us what it is that we would like to know. And now I'm going to show you something about the data that we collected. So pretty quickly, I have time and temperature, just like the old telephone thing. And the time at 1:32 was, the temperature was 55. At 4:51, so that's a little more than 3 minutes later, the temperature was 86, so the difference was 21. And at 8:42, that's 4 minutes later about, the temperature was up to 100, so that is a difference of, I can do arithmetic in my head, can't I? 14. So the rate of change, when the temperature was far away, we got about 7 degrees per minute. And when the temperature started to get closer, we cut this down to below 4 degrees a minute. That's Newton's law of cooling. So, bon appetit!